Uh, Good morning. This is Alan Migdal, and it's a great honor to introduce Jim Franson for today's talk. Give you a little background. He started with at Purdue for his bachelor's, and then got his PhD from Caltech, and then uh, also managed to do a stint with the U.S. Army Corps of Engineers doing reactor engineering. I guess I'll save questions about that uh, uh, for the questions at the end. And then he really got his start at Hopkins Applied Physics Lab, where he spent a number of years before moving to University of Maryland, Baltimore County since 2006. He is a fellow of the Optical Society of America and the APS, as well as most recently a presidential research professor. This fellow has an impressive history in quantum optics and fundamental physics. He is, of course, the Franson of the Franson interferometer, and it's a serious interferometer, not just like um, a single beam splitter interferometer, like which somehow got a name attached with it. Uh, his efforts have been both theory and experimental. His group was the first to demonstrate quantum cryptography in optical fibers, as well as the first demonstration of quantum logic using photons as bits or qubits. He's also pioneered the use of nonlinear optics effects, such as using the quantum Zeno effect to suppress failure events, which ordinarily would result in errors, essentially using those type of errors to your advantage. He's also did seminal work on multiplexed single photon sources, an area dear to my heart, and always has interesting perspectives, including a paper where he talks about not entangled photons, but entangled photon holes. Um, and in addition to his work on entanglement and quantum information, he's also involved in theoretical research in a number of other areas, including quantum mechanics and curved space-time, and the interface between quantum optics and quantum electrodynamics, and even has a paper with an apparent correction of the speed of light due to gravitational potential. And I really look forward to hearing what he's got to say. I always learn something. The floor is yours, Jim.
All right. Thank you, Alan. I'm glad this is being recorded. I can write that down and use it in the future, perhaps. Thank you very much. Also, thanks for inviting me here today to give this talk, and too bad we can't be in person. Besides the pandemic, we're having high winds in our area, and the electrical power went off about an hour ago. So if I disappear mysteriously, that's probably where I went. All right. So today I'm going to talk about violations of Bell's inequality using macroscopic states. And first, let me introduce our quantum optics group at UMBC. Todd Pittman is Professor Pittman is my longtime collaborator. And most of the work I'm going to talk about today was done by Ricky Brewster, who's now at a postdoc at College Park, and Ian Nodorf and Saurabh Srinigapour. So the motivation for this, and this is in fact a rather fundamental talk rather than applied. And of course, as we all know, Einstein objected to various aspects of quantum mechanics, and he famously said that God does not play dice with the universe. And he felt instead there should be some more detailed theory that explains all the random events that seem to be random, but in his opinion, were not random. And he also objected to the non-local collapse of the wave function, or which he referred to as spooky action at a distance. And so in response to these complaints, people studied theories known as local realistic theories or local hidden variable theories, which would explain all the randomness in quantum mechanics. So for about 30 years, that was really considered to be a philosophical objection. It Einstein didn't say quantum mechanics was wrong. He just interpreted it differently. But then eventually John Bell proved an inequality that showed actually there was an experimental difference between what Einstein believed in and what quantum mechanics predicts. And many experiments have been done, most of them using pairs of particles, and they agree with quantum mechanics, as you might expect. So the topic of interest today is, what about macroscopic states? Can we use Schrodinger cat states or high power laser beams or other macroscopic states to violate Bell's inequality? And I think this is an important question because quantum mechanics does a lot of counterintuitive things that seem very mysterious, and that's okay as long as it's down at the microscopic level of atoms and photons. If we had entangled, baseballs and all these things happen, then that might be a little more hard to imagine. So I think this does have to do a lot with what is the transition between the quantum world and the macroscopic world. So the outline is, I'll start out with a brief introduction to Bell's inequality for any students in the audience or people who aren't familiar with it. Then I'll talk about Schrodinger cat states and how do we generate Schrodinger cat states, which is not easy. Can they be used to violate Bell's inequality? And maybe even more importantly, can we protect them against loss and decoherence, because they are notoriously difficult to protect against loss. And then if time permits, I'll also talk about protecting quantum states against dispersion in optical fibers. So we may or may not get to this topic. So the idea is to start out very simple and then add more and more details. And so by the end, it'll be totally incomprehensible. No, actually, that's not the plan. I hope it's understandable throughout. And please ask questions if you have any. So we'll start out with a review of Bell's inequality. And maybe as an introduction to that, we can talk about the collapse of the wave function. And my favorite example of the collapse of the wave function is we have a single photon that goes through an interferometer with two different paths. And these paths could be very far apart. And we recombine them on a beam splitter. And we measure an interference pattern that depends on the difference in phase of this path and that path. And so intuitively, something has to travel along both of these paths in order to measure the phase on both paths. So really, the photon does go both ways at once. But then if we put a detector in this path and check to see if a photon is there, and if we find one, then the photon is there, and whatever it was in the other path disappears instantaneously, which Einstein did not care for. And that is true no matter how far apart these paths are. And in some of the experiments I'm going to talk about shortly, they've been separated by up to 25 kilometers. So it really is a long distance collapse of wave function. Now, however strange this collapse may seem, this is still consistent with hidden variable theories that Einstein advocated. And so, for example, de Broglie came up with a pilot wave theory where the photon doesn't travel down both paths, but some kind of a wave does. So this kind of experiment is still consistent with what Einstein believed. Now, if you want something that's inconsistent with what Einstein believed in, what you need are two photons and two interferometers. And we'll suppose that these interferometers are very far apart, and they've been up to 25 kilometers apart. And instead of one photon, we have two photons that are entangled that travel off to these interferometers and go through. And you may notice one path is longer than the other one, and there's a phase shift phi1 in one of them and phi2 in the other. Now, the source of the photons is a nonlinear crystal that we pass a high-intensity laser beam through it. And there's a very small probability that a single photon in the laser beam will be split off in two directions and create these two photons, a pair of photons. And that happens essentially instantaneously. So these photons come out at the same time. But we don't know what that time is. It's totally uncertain. And in fact, we have a coherent superposition of all possible times. And so this is an entangled state. And it's called an energy time entanglement. So anyway, what we do is in this experiment is we only accept photons that arrive at the same time in these detectors, coincident events. And since they were emitted at the same time and detected at the same time, they must have traveled the same distance. And so both of them must have went along the longer paths, or both of them must have went along the shorter paths. And we can have quantum interference between those probability amplitudes, which is non-local and gives a coincidence counting rate that depends on cosine squared of the sum of the two angles. Now, classically, you might think whether the light comes out here or here would only depend on this phase setting. But in fact, in quantum mechanics, what comes out here and here also depends on this angle, no matter how far away it is. And so this violates locality. So this is one way to show violations of Bell's inequality. And what Bell suggested was that we could collect coincidence counting date with two different settings of these phases, phi1 and phi2, in the two interferometers. So you vary these phases at random between two different settings and measure the coincidence rate. And then you can define a parameter S, which I won't bother to go through the definition of it, but nevertheless, it's based on this data. And if this parameter is greater than 2, then Bell showed that these results would be inconsistent with any theory of the type that Einstein advocated, any hidden variable theory. And so roughly speaking, what this means is that any classical interpretation of these kinds of experiments would require instantaneous communication between the two different points, which is certainly something Einstein would not have liked. So that's past history. What we're really interested in today, and we've been looking into this for several years in our group, is what about macroscopic states? Could we take, for example, a Schrodinger cat or two Schrodinger cats, entangle them somehow, send one this way, send one that way, and then somehow violate Bell's inequality using some kind of an interferometer? It turns out in principle you can do that, but it's not easy. And the reasons are that, first of all, you have to generate the cat states somehow, entangled cat states, and that's not especially easy. Then you have to find some kind of an interferometer that would violate Bell's inequality, and the one shown here would not work because some of the photons would go one way and some would go the other, and you just get a mixed state coming out. And finally, we would have to protect these cats from loss and absorption and other kinds of decoherence. So in principle, it can be done, although it's not easy. And so what we're going to talk about is ways in which this can be done. All right, so enough introduction about Bell's inequality. And now I'd like to introduce the idea of Schrodinger cat states in quantum optics. And this is based on a paper that we published a couple of months ago in PhysRev A. Saurabh Sringapur was the lead researcher on this paper. So before we get into the cat states, let's introduce coherent states for those of you that are not that familiar with quantum optics. And in quantum optics, a so-called coherent state, denoted alpha, is the closest thing we can come to a classical beam of light. And in fact, it is what comes out of a laser. And by definition, it's equal to a sum over all different numbers of photons. Here, this designates n photons in the field, with a coefficient which is this parameter alpha, which is a complex number with an amplitude and a phase. And what we have then is a sum over all n, and then we have alpha to the power n and the square root of n factorial. So that's the definition of a coherent state. And of course, the laser beam can be very powerful. So these states can be macroscopic. You can see them with your eyes and so on. And they have a lot of very useful properties in the derivations that we do, which I'm not going to go through. But one of them is that if you take the operator A that annihilates a photon and you act on one of these coherent states, you get back the same state multiplied by the number alpha. So these are eigenstates of the photon annihilation operator. Another thing that I should introduce are the idea of wave functions and quadratures in quantum optics. And the point is that a single mode of the electromagnetic field is equivalent to a harmonic oscillator, or mathematically equivalent. And when you second quantize it, you get raising and lowering operators, A adjoint and A, for the harmonic oscillators, which turn out to create and annihilate photons. So that's, I think everyone's pretty familiar with that. What we do in quantum optics is we define two new operators, X and P, which are either A plus A adjoint or A minus A adjoint. And if we had real harmonic oscillators, these really would be the momentum and position of the particle in the oscillator. But in quantum optics, some of you may recognize that A plus A adjoint is proportional to the electric field, and A minus A adjoint is proportional to its time rate of change. So we can think of these so-called quadrature operators as measuring the electric field itself. And these can be directly measured using homodyne techniques. So finally, we can introduce a wave function, which is the projection of the quantum state we have onto an eigenstate of this variable x, and we can call that psi of x. And so in this sense, the photons really do have a precisely defined wave function for a single mode. Okay, now we can finally get on to the Schrodinger cat states. And the most commonly...
Jim, it's Charles here. If I can ask a question.
Sure.
So I guess if one can look at this by just taking, here's this diagram of these two Mach-Zehnder, chained Mach-Zehnder type interferometers,
right,
and just regard that as an electromagnetic cavity and do quantization in it. And so the photon modes would correspond to, say, classical standing waves within it, and then putting a number of photons in the same state is just like saying, putting two photons in the same state is like saying that mode has double occupancy.
That's exactly right.
Does that way of describing it I mean, it's simplistic. Does it misstate anything?
The only thing it misses is, first of all, there's two different modes because photons are going in different directions. And then in that particular problem, it's also important to have an infinite number of modes because it all has to do with phases and the entire electric field. So yeah, it's a bit more complicated than just two photons in a cavity.
But it's a multi-mode, if you say it's multi-mode cavity.
Right, a multi-mode cavity is equivalent to that, right? Exactly.
Thank you.
Sure. All right, so the cat state typically defined as a coherent state alpha plus a superposition with a coherent state with the opposite amplitude minus alpha. And then we can include an arbitrary phase factor e to the I theta and a normalizing constant. So this is our cat state. And we'll be concerned quite a bit with what happens to a cat state if we pass it through a beam splitter. So here's a cat state like that going through the beam splitter. And then in the other mode, we'll assume we have the vacuum state coming here. So in terms of these quadratures, there's the so-called X quadrature for beam 1 and the X quadrature for beam 2. And if you plot the probability distribution of the electric field or the quadrature, you see there are these two separate components corresponding to alpha and minus alpha. Now, when we pass it through the beam splitter, it turns out this is changed and shown here. And if you look at this, you'll see that these are now correlated or entangled. And that can be both good in some sense because it makes entanglement that we can measure. It can also be bad because some of the information in this cat state is going to go off in the other path here. And that which path information could be measured and tell you which component you have. Is it the one on the left or the one on the right? And that would tend to destroy the interference. So this kind of entanglement shown here is both good and bad in terms of what we'd like to do. Now, the origin for the effects we're going to talk about today go back a few years and have to do with the following question about number states. That is, a state that has a definite number of photons. Now, photon number and phase are conjugate variables, and therefore the phase of a number state is totally uncertain. But one might ask, does that mean the number state has a specific phase and we just don't know what it is, or that the phase of a number state is just totally ill-defined? So that you can understand from the following type of experiment where we have a number state coming to a beam splitter and the vacuum coming here. And the beam that comes out here, whatever it is, we split off a small amount of its field and measure its phase. And it turns out when you do that, you can show that the remainder of the field coming out here is collapsed to a coherent state instantly. And that coherent state has the same phase that was measured up here. And then what's even more interesting is that when you do that here, you collapse the other beam to a coherent state with the same phase that you measured here. So you measure this phase here, you measure that phase there. And so in some sense, a number state has a well-defined phase. We don't know what it is. But if you split it in two and measure the phase one place, it's got the same value in the other place.
Jim, this is Bill.
Yeah, Bill.
So maybe it's just a philosophical difference, but when you say that this procedure that you've described, which I completely agree with, then tells you that the number state has a well-defined phase that you simply don't know, sounds to me like that's equivalent to saying, let's imagine that I've got a wave function of an electron that is spread out over some large region of space, and when I measure it, I get a value, and so that means that that was its value before I measured it, and we know that that's not right, or at least we've been taught that that's not right, and it doesn't sound like this is any different philosophically from that. So could you say more about that?
Well, actually, I agree with you entirely. And so, however I phrased it, I don't agree with that anymore. Okay. Yes, we have a superposition of all possible phases, and we don't know what it is. And in some sense, they all exist until we measure it. But the point is,
fine.
Yeah, but whatever it is, you can split it in two and measure it in two different places. Okay.
Yeah.
That's
But of
all.
course, there's also this point that for some kinds of quantum states, as you pointed out, for a single particle state, it was perfectly reasonable to assume a hidden variable theory where it does have a phase that you just don't know. But when you get two, then you are no longer allowed to do that.
Right.
Now, is this like that?
Yeah, this is like that. It's like the latter situation where now we have two because we have these two beams shown here, and they are entangled, and we can violate Bell's inequality and so on. So we really can't think of, okay, the phase was this or the phase was that. It's really all phases at once, but correlated.
Okay. Now, since I've got you, one more thing.
Yeah.
People use different terminology to describe what is meant by a cat. Now, you've used the terminology that I typically use, namely that a cat is a superposition of two sort of macroscopic states. Now, you can argue about whether it's a kitten or even an embryonic kitten, but still, it's macroscopic in some sense, in the sense that it's got, say, in your case, lots of photons, or at least the average number is lots of photons. That's what makes it macroscopic in some sense. Other people will say that isn't quite a cat. A cat is the superposition of two macroscopic states entangled with the superposition of some, say, microscopic state. In other words, in Schrodinger's original way of thinking, it wasn't the superposition of the live and dead cats. It was the additional entanglement with whether or not the gamma ray had been emitted or not.
Right.
And now, you know, that's not a huge difference, but that idea of entanglement is in there. But now you're introducing entanglement of a different sort. I just wanted to make sure I was following correctly. You've entangled these things, but that's an entanglement of a different sort than the type that is sort of, I guess, a technical issue about what you're going to call a cat or not a cat.
Well, actually, I agree with you once again. And we start out with a state like two cats that really are entangled only with themselves, and then they interact with the gamma ray or whatever. And in our case, they're going to interact with something that will indeed entangle them with another system. So we're going to have all of the features that you just mentioned shortly.
Okay, well, I'll just wait then and see how it pans out.
Okay. Anyway, so the idea is that we may have this phase in one beam and the same in the other, a different phase in this one and the same in that. And then we have a superposition of all of these. And so this is an entangled state. And cats usually only have a superposition of two possible phases, but here we have a superposition of all possible different phases. Now, mathematically, I'm not going to go into any equations. This may be the only equations I show today, but this can be described mathematically in the sense that a number state can be written as an integral from 0 to 2 pi of all possible angles, some function of the angle over here, and then a coherent state with an amplitude r and a phase phi. So the original coherent state really is a superposition of all possible phases to begin with. And so the state incident on the beam splitter can be written as the sum over all possible phases, this coherent state in beam 1, and the vacuum state in beam 2, which corresponds to alpha equals 0 in that case. Now we know in quantum optics that a beam splitter will take a coherent state and generate 2 more coherent states in the 2 paths with amplitudes that agree with classical physics. And so what happens then is that this state here becomes a reduced amplitude in one path and the similar amplitude in the other path if we have a 50-50 beam splitter. So mathematically then this shows, yes indeed, we have a state where we have a coherent state in both paths, but we have a superposition of all possible phases. Now the key is, how can we make an interferometer out of this that might violate Bell's inequality? And so the idea is shown here. It's a bit of a busy diagram, but suppose we can somehow apply a random phase shift of plus or minus theta to both beams. And then suppose we also only accept or post-select on events where the final phase is found to be 0, okay, which would be here. Now, there are 2 ways that could happen. One is that the state may have originally had a phase of minus theta, and then we shifted it by plus theta to get it back to 0. Or it might have originally had a phase of plus a theta, and then we shifted it by minus theta to get back to here. Now, remember, we have all these possible phases, but the only one that contributes to this particular process are where we started here, or we started there, and we ended up back here. And what we'll find is that we can, once again, get quantum interference between these 2 probability amplitudes, whether we started in the purple area or started in the red area, 2 different ways to get the same result. And that, we'll see, violates the Bell's inequality. Now, how can we do that? And that's shown here. We have our number state coming onto a beam splitter. It makes this entangled state with correlated phases. It travels a long, long distance, many kilometers, let's say, and then it comes to a single photon interferometer shown in red. So we take a single photon, send it to a beam splitter. It either goes this way or that way, and we detect it in one of these detectors. And in one path, we assume we put a Kerr medium. And Kerr medium is a device that can produce a nonlinear phase shift, so that if the photon goes through this path, we get a phase shift of plus theta. And if it goes through the other path, we get a phase shift of minus theta. So that's how we can introduce these phase shifts of plus or minus theta, depending on which way the single photon went. And then, once again, we post-select on a net phase shift of 0, which could happen in 2 different ways. Started here, get shifted backwards. Start there, get shifted forwards. And the post-selection excludes these other events here, which are represented by an X. So we don't accept that. We only accept this in the end. So if you go through the analysis, what you find is that the probability of this occurring is, once again, proportional to the cosine squared of the sum of the 2 phase shifts in these paths. Here's a sigma 1 phase shift, and here's a sigma 2 phase shift. And so we get this cosine squared dependence, just like or similar to the first interferometer. And the question is, does this really violate Bell's inequality? Because we need to worry about how many photons do we have, how much loss do we have, and a lot of other issues. But that's the basic idea. 2 single photon interferometers that produce a phase shift plus minus theta, and then we get quantum interference between those 2 paths. So the first thing is, can we do a post-selection of the kind that I just showed using this state that we started with? And this shows actually the wave function squared of the state as a function of the 2 quadratures, x1 and x2, in the 2 beams. And these correspond to the cases where both paths were shifted positively, so we call that psi plus plus. And that turns out to be equal to the same wave function for psi minus minus, both shifted minus in the minus direction. And this is what we want to accept in our post-selection process. We want to get interference between psi plus plus and psi minus minus. Over here is shown the corresponding wave function squared for the case where one was shifted positively and the other negatively, and we'd like to reject this. And you can see there are a lot of places where this one has a nice value. It's not 0, and this one is exponentially small. So all this really shows then is we can do the post-selection on this state and eliminate the probability amplitudes that we don't want and keep only the quantum interference terms that we do want. Now, what we can do then is vary these phase shifts, sigma 1 and sigma 2, and plot what happens. So if we hold phase shift number 2 in one interferometer at 0, and to vary the other phase shift, we get a cosine squared type curve. And if we hold the phase in the other one at pi instead and vary it, then we get a sinusoidal squared type of curve. So this looks promising. Typically, when you see these kind of curves in quantum optics, you know you're on your way to violating Bell's inequality, other than perhaps some difficulties, which in our case might have to do with what happens to the photons due to photon loss. So this looks promising. And so what we did was we looked at the Clauser-Horn-Shimoni-Holt form of the Bell's inequality, which is easier to use experimentally. And once again, if this parameter S is greater than or equal to 2, the Bell's inequality is violated, and there is no local hidden variable theory that could agree with the data. So what's plotted here is, recall there are 4 different angles, 2 here and 2 there. And 2 of them are held fixed, and we vary the other 2 and plot the magnitude of this parameter S. And anything above this sort of medium-looking orange color violates Bell's inequality, and that turns out to be throughout this whole region here and here. So yes, this system can, in principle, violate Bell's inequality. And in this case, the plot corresponds to 4 photons incident on the initial beam splitter. And that's something we could produce in the lab with some difficulty, but we can produce it. So what happens, though, if we have even smaller numbers of photons, and that's shown here? Here we're going to vary the number of photons incident on the beam splitter. So the more we have, the more macroscopic the state is. The smaller it is, the easier it is to make the state. And the upper curve corresponds to the ideal situation where we're not worrying about a loss or anything else. And the interesting thing is that you can violate Bell's inequality by a small amount, even with just one photon incident on the beam splitter. And then it gets better and better as you go up in larger numbers of photons, and then approaches the limit allowed by quantum mechanics. Thankfully, our calculations did not go above that line. Otherwise, we'd have problems. Then what these other curves correspond to is the fact that you can't really post-select on a phase shift of exactly 0. You need some window, plus or minus a certain amount. And if you vary that window here in radians, we get these different violations also. And it turns out it's not very sensitive to the width of the window. So that's good. But now the key question might be, what about photon loss? And you can model that with a beam splitter. Like I showed before, the cat state comes in to the vacuum state here. And the decoherence is literally due to the fact that information is going to be left in the environment here. Some of it is split off, and if you measured that, you could determine which of these phases you actually have. So as a result of that, we've plotted the, as a function of the mean number of photons lost, n bar, and our parameter S, which needs to be 2 to violate the inequality. And what you can see is that if you lose even a fraction of a photon, 0.3 on average, then you can't violate Bell's inequality anymore. And so the experiment would be very challenging. Once again, this is due to which path information left in the environment. And so what I'm going to talk about next, and perhaps throughout the rest of the talk, is how do we eliminate that and restore all the coherence that we had to begin with. Maybe just briefly for the experts, mention that because we're using post-selection, you might suppose that we would have to use the so-called fair sampling assumption, which says that, okay, you're rejecting most of the data, and you're assuming that what you keep is representative of the rest of it. It turns out in this experiment, we don't need that assumption, provided we do the post-selection first, and then choose these phase shifts at random. So that's a minor technical detail. All right, let me summarize so far. If you pass a number state through a beam splitter, you'll create 2 beams coming out whose phases are highly correlated, and in fact, they're entangled in phase, and it's a generalized form of a Schrodinger cat state. You can get interference between those two different possible phase shifts by shifting them back to the origin, and this is a new kind of non-local interferometer, and it can be used to distribute pairs of macroscopic states and so forth. So that's the summary. That's all the good part. The more difficult part then is protecting these states against loss. And this is something that we discussed in a paper 2 or 3 years ago, and Ricky Brewster was the lead author on that one. All right, so what can you do about this loss? And the thing to keep in mind is it's due to the Witch path information left in the environment. And so Makuta and his colleagues proposed the following scheme. Suppose you take an arbitrary state that you want to transmit through a lossy channel like an optical fiber, and you noiselessly attenuate it down to a really low amplitude. And I'll explain how to do that in the next slide. Then you send it through the lossy channel, and then you put it through a noiseless amplifier, which restores the original amplitude, and the original state then comes out of here on the other end. So why does this eliminate the decoherence due to loss? Well, if you attenuate the state to the point where it has hardly any photons left, then you're not going to lose any photons in the environment. The environment doesn't get any information, and so there's no decoherence as a result of that. Okay, so first, how do we attenuate a beam without creating noise? And recall, if you just put it through a beam splitter, you create a great deal of decoherence because of the information left in the environment. So what Ricky realized was you could do this with an optical amplifier, of all things. Attenuate with an amplifier. So the idea is we have a strong pump laser beam goes through a nonlinear crystal. As before, a single photon in the pump beam can be split into 2 photons. One comes out here and one comes out there. Our signal comes in here. And whether you like it or not, there's another path, typically called the idler. And this device creates pairs of photons. One goes here and one goes there. And then if you send in a signal here by stimulated emission, it will be amplified. And so an amplified beam will come out. Unfortunately, you also get entanglement with this other beam, which can cause noise and decoherence in the amplifier. So what we realized was that you could avoid all those problems if you put a detector in the idler path here, and there are no idler photons coming in, and we select a case where no idler photons come out. So nothing comes out of the idler path. And then we looked at what comes out of the signal path going through here. Now this seems a little counterintuitive because the photons we know are emitted and absorbed in pairs. And so if no photons came in here and none came out, we know the amplifier did not emit any photons, and we know it did not absorb any photons. And you might think, well, the amplifier did nothing at all. But it turns out that this state will actually be attenuated rather than amplified. So the results of the calculation are shown here. The actual calculation is lengthy and based on quasi-probability distributions, and you can look it up if you like, but the answer is shown here. If the input state is a coherent state alpha, then the state that comes out, aside from a normalizing constant, has an amplitude alpha divided by G, where G is the gain of the amplifier. And so what this shows is that in this kind of operation, this device reduces the amplitude by a factor of the gain rather than increasing it by a factor of the gain. And this does seem very counterintuitive. And what I think is really amazing is the fact that a coherent state comes out still a coherent state and not some more complicated thing.
Jim?
Anyway, yeah.
This is Bill again.
Hey,
now, if I've got an amplifier, I can, normally an amplifier will add noise.
Right.
But there is a case when you make the amplifier phase sensitive that you can do noiseless amplification. Now, what I'm wondering is this related to that? Is this, but in order for that to happen, it has to be phase sensitive. Now, here a de-amplifier is a lot like an amplifier. Is this like that? That is there somewhere here a phase sensitivity that allows the noiseless de-amplification, or is this something wholly different?
No, this is totally different from that. In this case, it's not phase sensitive. Any phase will do, and that's important in our case because recall we have superpositions of all different phases, right? So it has to be phase insensitive. And I'll show some results in a minute showing that it does work. So how this works is because the post-selection is a non-unitary process. And if you have a non-unitary process, you can violate a lot of principles that you might have thought were, cast in stone, such as amplifiers produce noise and so on. So this really is different than a phase-sensitive amplifier. It's got a non-unitary transformation.
Okay.
Okay, yeah. How does this work? Okay, we just said this amplifier doesn't do anything. It doesn't add photons. It doesn't subtract photons. What does it do? And the answer is we start out with a state that has a superposition of all possible different numbers of photons. And if you look at ones that correspond to a large number of photons, they're likely by stimulated emission to produce pairs and therefore not survive the post-selection process. But if you look at states that have a relatively small number of photons, they're less likely to emit a pair, and therefore they're more likely to survive the post-selection. So what this process does is it really just shifts the probability amplitudes around, makes some probability amplitudes more likely than they were to begin with, without any transfer of energy. It's just the selection process. Well, does this really work? And the thing to do is to try it out with a Schrodinger cat state. And this shows some data that Sorab calculated. Here's an original cat state. And by the way, this is the Wigner distribution that depends on X and P for a single mode. And the cat state has these two peaks originally. And in the Wigner distribution, however, they have long tails. And they overlap and cause some features here that represent quantum interference. And furthermore, the probability goes negative, or I should say the quasi-probability goes negative. So this is a good indication that this initial cat state is very non-classical. Now, if you put the cat state through an ordinary beam splitter, you see these peaks are coming closer together, but the features in the middle are being greatly reduced. And so the quantum interference is being destroyed by an ordinary beam splitter. Now, if you put it through the noiseless attenuator, instead what you see is the peaks still come closer together, but all this structure in the middle is still preserved. And finally, this is what you get for a perfect cat state whose amplitude was just less to begin with. And so these two are essentially identical. And so indeed, the noiseless attenuator does work on cat states and eliminates the decoherence.
Jim?
Yeah.
So just to help me clarify my understanding of what this noiseless attenuator does, you've presented it as being something where you put in a coherent state, and the coherent state is a superposition of lots of different number states, and then if you select on the coherent state happening to have fewer photons, you end up with a smaller number of photons, but because of the way you've done the selection, it still remains a coherent state, just with a smaller average number of photons. Right. Now, it seems like possibly a simpler way of doing it would be, let's say that I put my coherent state through a whole series of beam splitters that were only taking off a little bit each one. And I put photon detectors at each one of those beam splitters. Let's say there were 99 beam splitters, and I had a whole series of them, and I post-selected on the cases where none of those detectors fired on the 1% peel off. Would that be doing the same thing?
Yes. Once again, I agree with you completely, Bill. We're on the same track.
Okay, good.
It can be done that way, and another group proposed that first. And the reason I talk about the one shown here is just it seems so counterintuitive. Like,
okay.
Yeah, but you're exactly right. It can be done with a beam splitter, and experimentally it would probably be easier. Although,
okay, but it's hard to have lots and lots of beam splitters and lots and lots of detectors, but conceptually, at least, it seems easier. But that's just what you were going for, was the one that wasn't conceptually easy.
Exactly.
Okay,
Exactly.
great.
Yeah.
Can I
So,
ask a follow-up question to that? This is
oh
Alicia.
yeah, sure. Please do.
So how vital is it that this post-selection sort of be faithful, right? That detectors have a quantum efficiency, and if the mode matching to the detector is not good, then just because the detector didn't fire doesn't mean there wasn't something there.
Very good point. And one of my students did that calculation, and he has lots of all that too. And I just left it out because I think it's to be too complicated. But you're exactly right. As the detection efficiency is less, then this process is, not 100% correct. And that's why we need Alan and his colleagues to keep making us better and better detectors and characterize them and so on. So we need 99.9% if we want to get a fidelity of 99.9% in essence. Good point.
Okay, great, thank you.
Sure. Okay, so the remaining question then is we've attenuated the state. Now we want to restore it somehow. And Ralph and Lund proposed a noiseless amplifier, which I'm not going to go through the details of this. What I'll just say is that the device shown here is roughly equivalent to what I showed before, except its goal is to increase the probability amplitude for larger photons rather than decrease it. So it's still post-selection and very similar. The catch is if you want to send in a state with an arbitrarily high amplitude, this device here requires that the amplitude be much less than 1 or small. And so you have to split it up with beam splitters into multiple paths, apply this operation to each one of them, and then recombine it. And that works and has been done, but the problem is that there's some probability of success for this device, and if you have to have it succeed many, many times, then the probability starts to scale exponentially with the strength of the field that's coming in. So it works, but it is post-selection, and it doesn't always work. So now my favorite part about this whole approach is the question of where's the information? Where's the information gone? And suppose we take a macroscopic state that has n much greater than 1 bits of information, a cat state with a lot of information. And then we send it through this noiseless attenuator until it's very nearly equal to a vacuum state. Just almost no photons left at all, right? That's what we transmit through the fiber on purpose. Now, the vacuum state itself contains no information. Von Neumann entropy is 0. All it has is noise, fluctuations. So now we have a state which is almost nothing but fluctuations. And its entropy, if you measured it, its information would be almost no bits whatsoever. And nevertheless, sometimes we can successfully recover all n bits of information from a single one of these states, not the average over a lot, but a single one. And that may not happen very often, but nevertheless, one of these states carries all n bits of information. And so the paradoxical question is, where is that information? And maybe the first thing to note is that we did not split off any information into the environment. The attenuation is designed in such a way that we don't leave any information in the environment. Whatever information there is still left in the state, and we can get all n bits out of it in the end. So I'll leave this as a puzzle for you to think about, but to me it seems as if the measures of information, how many bits of information there are, doesn't really tell you how many bits of information are in the system, but also how difficult is it to extract it out of the system. So that's a paradox to think about, and I can see Alan is looking puzzled about this one. Anyway, you can think about it. Where's the information? Are there still n bits of information in that state or not?
Jim?
Yeah, Bill.
Since the n bits of information only get transmitted occasionally, that means most of the time something else is being transmitted, which presumably is not the original information.
Perhaps.
So in a sense, is this any better than noise?
It's better than pure noise because you can get the bits out sometimes. But
yeah, but you don't know whether it's good information or bad information, do you?
all we do when it works, you know it worked correctly, and these bits are all perfect. Okay.
I see.
So when this is probabilistic, but when it works, it's perfect. And then when this works, it's perfect, and you know it's perfect. And out come your n bits, all perfect out of this thing. Now, classically, you could probably average over a lot of these noisy signals and extract the information. But here we're not averaging because all the information comes out of just one transmission of this state.
Okay, it's weird.
It's weird. It's weird. So let me summarize this section then, and probably we don't have time for another section, but macroscopic quantum states are very sensitive to loss. That's well known. But we can reduce the decoherence to make it arbitrarily small if we attenuate it first and then amplify it noiselessly afterwards. This is probabilistic and doesn't happen very often, but we do know when it succeeds. And furthermore, we could send a cat state through a long fiber, reconstruct it in some sense, and then violate the Bell's inequality. All right, so I had planned to talk about another topic, which I think I'll skip over, and I thought perhaps I would have to. And let me just say very briefly, this is some work that we did recently this year to show that you can have cancellation of dispersion between two different beams that applies to more than 2 photons. So just one slide about it. If we have 2 classical pulses of light traveling through different optical fibers, those pulses will be spread out due to dispersion. And classically, what happens to this pulse has nothing to do with the other one, especially if they're 25 kilometers apart. But if the photons are entangled, then you can show that the dispersion in one fiber can be canceled out by the dispersion in the other one. And so there's no net dispersion left. And it can be shown that these kinds of results are inconsistent with any hidden variable model. So I'm going to skip this, except to say that we did this for the case of 3 photons and more, and lots of interesting plots and so on, but I'll skip through that. If anybody wants to ask questions about those, of course, we can go back. So just to summarize the talk in a whole, Schrodinger cats can be generated in a fairly straightforward way, just with a number state and a beam splitter. And experimentally, these are 2 of the most useful and available resources we have in the lab. We can make these number states, and we certainly have beam splitters. So that's very interesting. Then it's not obvious, but indeed, Bell's inequality can be violated using these kinds of states. And although it's very sensitive to photon loss, there are ways to minimize that in a probabilistic sense and transmit the state through a long fiber and then reconstruct it and violate the Bell's inequality. So I think I'll stop there and acknowledge my collaborators, Professor Pittman, Ian Nodorf, Sorb Sringapore, Ricky Brewster, who's now at College Park, and Brian Kirby, who's now at ARL. And this was funded in part by NSF and ARL. So thank you for your attention. I guess we have maybe a few minutes for questions. Thank you.
Send you, send you the sad Zoom applause.
I have a question.
Okay, Alan, you're on.
So to post-select, you actually have to send a lot of information across the channel. And to post-select where it's all 0, that's sort of like the most information you're sending. Is that not where the information gets shifted to?
You're asking where does the information go? And yeah, okay. So I will have to admit, I do not know if there's some theorem about information is conserved. That I really don't know. But if the laws of nature are invariant under time reversal, you would think so. I mean,
yeah.
I believe you could prove that. So what we have here are non-unitary transformations in essence, and that's how the information is kind of reduced on average, but it's still there in some sense, and we can detect all of it occasionally. I don't know if that was your question.
But, well, if we go back to the model of having a whole bunch of beam splitters and detectors, that if it goes through a whole bunch of beam splitters and detectors, and you've selected out the ones where none of the detectors fire, that's a lot of information, isn't it?
in the sense that the detectors did not fire?
Right.
Okay, so the von Neumann entropy of a state where we have 0 photons and all the outputs is 0 bits, I believe. I'm not an expert on that, but I think that's
Well,
true.
So I guess what I'm thinking of is like with a thermal state. If you have a beam splitter and your detector clicks, you now know that the transmitted beam actually has a higher than its original mean photon number. And if it doesn't click, it seems like conversely, you know that it has less. And if I picked off 100 splittings and I got nothing, it seems then I know a lot about that transmitted beam, even though nothing was clicked.
But maybe that's a good interpretation, although it's not as weird as my interpretation, so I don't like it as well.
Okay. All right.
There might be a lot of truth in it, though.
Okay.
So I've got a question about the last thing that you teased us with, the dispersion.
Okay, good.
So I mean, basically, what I'm wondering is whether this might be good for something, and I'm wondering what it might be good for. Would be GPS. Now, as you know, GPS relies on really accurate clocks, and as we make clocks better, we might think that we're improving GPS, but there's a problem, and that is dispersion. The signals that go up and down from and to the satellites go through dispersive medium. You got all kinds of stuff in the atmosphere and the radiation belts and stuff like that. And the way that's dealt with is you send different frequencies, and by seeing how the phase shift of the different frequencies works out, you can work out what the dispersion is and make a correction for it. But of course, that only works so well. So what I'm wondering is, will this be a magical way of fixing dispersion?
Yes, actually, it's been papers, a lot of papers written about what all you could do with it. One is synchronizing clocks in particular. Others is in QKD applications where, if you spread out the pulses, you're essentially reducing the bandwidth. I believe there have been papers written about, and maybe even experiments where you send photons into a human's eyeball to make images, and this dispersion cancellation reduces the effects of all the globs of stuff in your eye, whatever they are. So yeah, there are a lot of possible applications of it.
Well, maybe I can fit one more question in, since I don't hear anybody else. So going back to the first part, you presented it as basically a fundamental investigation. What I'm wondering is it good for anything? That is there a way in which you could use this to do, say, better quantum key distribution or something like that? Because it sounds like it's tough because of the fact that you got to do all this post selection, and that's going to make the whole thing inefficient. So I'm wondering whether there's something good that you could do in a practical way for this.
I think there is, and the first thing that comes to mind would be quantum sensors. You may want to probe a distant object, sending, let's say, entangled state, and what you want to measure is maybe a change in the index of refraction in some area, or some absorption, or whatever. And so the more macroscopic the state is, the more sensitive it would be to those kinds of things. So that might be one area of application. In terms of QKD, it does have the interesting feature that we send a lot of bits, and occasionally we get all of those bits, and we're essentially guaranteed that the eavesdropper cannot get any, no matter what he does, because we're arbitrarily close to the vacuum state in between. So I think it does have some possible applications of that kind.